Hello, my name is Dan Oake and I'm a student at Athabasca University, and I'm currently taking the course Computer Science 444 Embedded/Robotic Programming. And if you've been following the videos I've been posting to the course forum so far, you'll know that I'm going through the SparkFun Inventors Kit guide, which is associated with the SparkFun Inventors Kit, which comes with a generic Arduino type microcontroller, specifically the RedBoard by SparkFun, a breadboard, and a lot of sensors and actuators and other components that you can use to make a lot of fun projects, including the project that we'll be talking about today, which is Project 2, specifically Circuit 2B and 2C. So in the previous video series, I went through Project 1 and the 4 circuits associated with that, and then in this video series, I've started to go through Project 2. I already have one video with Project 2's Circuit 2A, the first circuit of Project 2, which dealt with a buzzer. And then in the last video, I went through Circuit 2B, which was a buzzer and buttons called the button Trumpet. But I never quite got through it because, frankly, I had to take my daughter to a doctor's appointment, and so just we had to cut the video short. So I got through a lot of the code, but I didn't actually show the demo. So that's what I'm going to do in today's video. I'm just going to finish that up, and then I'm going to move on to circuit 2C, so the third part of the circuit. So I already did go through a lot of the code, but I'm going to revamp it a little bit here just so to catch everyone up, but you might want to watch that previous video. So as usual, I have some Doxygen comments. That's what this extra asterisk is. It just is a multi-line comment, but by putting this extra asterisk here, it makes it a Doxygen comment, which means I can put this through a program, an external program like Doxygen, and it'll create some, professional HTML documentation for this program for me. Again, if I lose that asterisk, it's just a regular multi-line comment, starting with / asterisk and then comments for however many lines I want, and ending with an asterisk /. That's a regular multi-line comment. But by putting this extra asterisk here, it makes it a special type of comment that can be read by another program and make those automatically generate those HTML documents for me. For anyone who's familiar with Java, it's essentially JavaDocs commenting. And that's also why I have 3 / here for these inline comments. Again, if it was just 2 / it would be a regular inline comment, but these 3 / make it a Doxygen type comment, capable of generating those files, which is why the color changed in these tags as well. As I said, I've already mentioned this in the previous video, but these are all my constants for all of my pins. So I have three pins associated with 3 different push buttons, pin associated with the buzzer, and 3 pins associated with LEDs, 3 LEDs, a red, a green, and a blue. Truth be told, it's actually just a single LED that I'm going to be using in today's video, an RGB LED, which is again just a single LED, but it's capable. But it's technically inside this one RGB housing are 3 small LEDs, a red, a green, and a blue. And go back to this. So in the coding challenge, what our goal was in the original circuit, we had 3 different buttons, and when you pressed on the different buttons, it activated different tones. So if you press button 1, it outputted the frequency via the tone function that is associated with note C. Button 2 was note E, and button 3 was note G. So that was the original circuit. For the coding challenge, we wanted to be able to play more than 3 notes with either if statements or binary math. So in the previous video, I think I went over more of the binary math, but I've since then added some if statement logic with some Boolean AND operators. And basically, by using combination of the buttons, we'll be able to output more than just the 3 notes, which we were doing previously by each button representing a single note. And I've also added the RGB as well. So again, back to the code, that's what the constants are for: my buttons, my buzzer, and my LEDs. I also have constants for all of the notes, so note C through B with the corresponding frequencies, and I've set those all up as constants. In setup, I just call the pin mode function, setting everything up. So I set up my buttons as inputs, and I'm using the argument input underscore pull up, which sets the buttons up as inputs, but also activates the internal pull up associated with the RedBoard microcontroller. This way, I don't have floating values for my button pins, but rather they're always held high to 5 volts when not pressed, and they'll go low or 0 volts when activated. I've also got my 3 LEDs set up as outputs as normal, and my buzzer pin where my piezoelectric speaker is hooked up to as an output. In the loop, I'm calling a digital read function on all 3 of the buttons. So first key pin, the first button, and I'm checking to see if it's equal to low. So this double equal sign indicates equality, the Boolean operator equality, as opposed to a single equal sign, which is just an assignment operator. So this is basically reading the pin that the first button is attached to and seeing if it's low, which means and what does this mean? This means, check if first button pressed, because if it's pressed, it'll be low. If it's pressed, whatever we get as a value here, this statement is going to return true or false. We're going to assign that to the Boolean variable first key pressed. So it'll be true if the button was pressed and false otherwise, and we'll do that for each of the other buttons as well. And then we're going to call this setRGBColor function that passes in those 3 Boolean variables representing whether the first, second, or third buttons were pressed to our helper function we've created called setRGBColor. So if I jump right to that function, setRGBColor, as you can tell by the Doxygen style comments, it has 3 parameters: red state, green state, and blue state, and this determines whether the red button is pressed, the green button is pressed, and the blue button is pressed. So we pass in those 3 Boolean arguments into the function, and the function doesn't return anything, but what the function does do is it calls digital write on those 3 pins, on the red LED pin, the green LED pin, and the blue LED pin. And what state does it send? Because remember, digital write can either send a high or low state, i.e. turning the pin on or off. And because there's an LED on that pin, essentially turning the LED on or off. But we've got this weird syntax in here instead of just the word low or high. If you're not familiar with this is called a tertiary operator, and it's basically a shorthand way to do an if-else statement, but very compactly. So basically, what happens here is we write something that's a Boolean, or something that will evaluate to a Boolean, true or false, which in this case is red state, which is a Boolean, so this will be either true or false. And if it's true, we're going to put high in place of this whole thing. If it's false, we're going to put low. So that's what this question mark says. This question mark basically says if, then true, then do this. Else, so this colon is like else do this. So again, we're evaluating this Boolean, or this could be an expression that evaluates to true or false, and then if it's true, we do what's after this question mark, which is high. If it's false, we do what's after this colon, which is low. So ultimately, all of this entire tertiary operator syntax right here is going to be replaced with high if the red state is high, meaning if the button is pressed, or it's going to get replaced low if the button wasn't pressed. So basically, that's what these 3 digital write functions are doing. They're turning the LED on if the corresponding colored button has been pressed, and low or off otherwise. So then back to where we called that in the code. And then I have 2 options. So play tones based on button combinations. That's ultimately what we're going to do, but we have 2 options for doing that. Option 1 is using if statements with the Boolean AND operator to handle combinations, which I have commented out for now. And the second option is to use binary math to calculate the unique identifiers. So this is what I showed in the previous video, so I'm just going to restart with that one. Basically, I am using Boolean math, which you can look up. I won't bog down this video with that, but for anyone who's familiar with Boolean logic, which presumably if you're taking this course you are, but I'll give a quick overview right quick. I've said quick about 4 times there. So for anyone familiar with how Boolean, or not Booleanary, rather binary works, binary means that there's 2 states, bi for 2. So 2 states, so it's a base 2 number system. So 2 states in binary, base 2 number system, as opposed to the number system we use every day, decimal number system, which is dec, 10. It's a base 10 number system. So with base 2 number systems, we have 2 possibilities for each option, let's say. And if we have 3 buttons, that's 3 options, we find out how many different combinations we can make from that by going 2 to the third power, which equals 8. So again, each button, I have 3 buttons in a circuit, each has 2 possible states. It can be high or low, on or off, pressed or not pressed. So there's 2 states, it's binary. But I have 3 different buttons, so 2 to the third options, I have 8 different possibilities that can be made. Now what are those 8 different possibilities? Well, they could all be off. These are zeros. They could all be in a state of off. The first 2 buttons could be off, and the last one could be on. So 0 and 1 for binary. The middle one could be on, and the other one's off. This one could be on, and these 2 off. Actually, let me just do this properly. Just read that. These 2 could be on, and this off. This one could be on, and these 2 off. These 2 on, and this off. These 2 on, and this off, or all 3 of them on. And so that's 1, 2, 3, 4, 5, 6, 7, 8. 8 different states. So one of the states is just all of them off, but the 3 different states of light combinations are the 7 remaining, 2 through 8. Now, this is how you count binary. So this is binary. This binary representation here corresponds to decimal 1, and this corresponds to decimal 2, and decimal 3, 4, 5, 6, 7. I understand I've made this a lot more confusing than it needed to be, but that's a very rudimentary and very forced, I would say, quick representation of what's happening in binary with the code here. But hopefully you'll be able to see it. Maybe I'll try to do this a little better and do a side-by-side. I really do want you to understand what we're doing here. So I'm going to make this just a little bit bigger. Okay, so again, counting in binary, this is binary 1. This is decimal 2, 3, 4, 5, 6, 7, how we normally count. The binary representation with 3 states, 3 different buttons, is that's 1, that's 2, that's 3, that's 4, that's 5, that's 6, and that's 7, all of them on. So we'll see how this compares. So in this particular case, we're going to take our first key press, which is our button 1. Let's say this button here, this is button in the button 1 position, this is button 2 and button 3 position. We're going to take button 1 and we're going to times it by 1. So whatever the value of button 1 is, we're going to times that by 1. We're going to take the second key pressed and take that value and times it by 2, and take the third key pressed value and times that by 4. So what's that going to do? And what's this first key press thing? What variable is that? Well, let's go look. Again, first key pressed is this Boolean variable here, which is going to be true or false, which corresponds to 1 or 0. 0 for false, 1 for true. So if the first key is pressed, that's going to be a 1. Well, 1 times 1 is 1. And if neither of the other keys are pressed, that's going to be just 0 times 2 and 0 times 4. So we're going to get 1 overall. In which case we're going to go to case number 1. Because combination will be 1 plus 0 plus 0, which is 1, and that's the combination. And then we're going to go into our switch statement, passing in combination, which is going to be a 1 in that case. And we're going to call case 1, which means we're going to play tone note C. This is a constant. And then break out of this switch statement. So what is case 1? Well, that's the red button, note C, meaning if I just press button 1, the red button. Again, button 1 is that red button, in case you need to refamiliarize yourself. Then, if button 2 is pressed only, so the yellow button 2 is pressed only, which is here, it'll be times by 2. So again, if second key pressed, we times that by 2, so that's 1 times 2 is 2. And if both the first and third buttons aren't pressed, which they're not, 0 and 0, then 0 plus 2 plus 0 is 2. So then we're going to go to this case number 2, where the green button was pressed. I got these mixed up a little, but the green button is pressed. Oh, quick correction. Why I have red, green, and blue here is I was going off my RGB colors. So I should just replace those buttons right quick and make it RGB. There you go. So button 2, if just the green button is pressed, that's going to play note D. Then, case 3, so we're jumping case 4 for a minute. We're going to case 3. I'm not sure how I messed that up, but anyway. If you're going to case 3, that means that the red and the green button, oh, that's why, sorry. Case 4 was just the blue button pressed. And I'll show you why that's case 4, because if the first key is not pressed, that'll be false, which is 0. 0 times 1 is 0. Plus the second key isn't pressed. 0 times 2 is 0. So 0 plus 0 is 0 so far. But if the third key is pressed, that blue button, we take that value times it by 4. And again, the value of true is 1. So 1 times 4 is 4. So that's why we get case 4 if just the blue button is pressed and we play, and we'll put note E. Now, for case 3, that means that so this was case 1, case 2, and this is case 4, where just the blue button is pressed, right? Just the blue, just the red, and just the green. Now, for case 3, that's when both the red and green button are pressed. So, again, red being the first button, green being the second button. So, if both those buttons are pressed, well, we're going to have 1 times 1, which is 1, plus 1 times 2, which is 2. So 1 plus 2 is 3, and this button wasn't pressed, so this will evaluate to 0. So that's where we get 3. And that's basically the formula that's being followed here. So then for case 5, we get the red and blue button is pressed. So again, that's the first button, which is red, and the third button, which is blue. So 1 times 1 is 1, 0, plus 1 times 4, which is 4. 4 plus 1 is 5. And then similarly, when the green and blue buttons are pressed, 1 times 2 is 2, plus 1 times 4 is 4, 2 plus 4 is 6. And finally, if all 3 buttons are pressed, 1 times 1 plus 1 times 2 plus 1 times 4, well, that's 1 plus 2 plus 4, that's 7. And then if no buttons are pressed, we're going to have silence. We're going to call the no tone function, passing in buzzer pin as the argument, and break out of this. So I understand that's fairly confusing, but we'll just finish this up. And then finally, we have this function called play tone, which is really just an encapsulation of the tone function that's built in to the Arduino program. So the tone function takes in 2 parameters, the pin that the speaker is attached to, and the frequency that you want to output on that speaker. And so my play tone function simply takes in a frequency, so an int type argument, and passes that in to the tone function as the frequency, and we automatically just call the buzzer function. So again, the play tone function is really just a helper function I created that encapsulates the tone function and just used for clarity in the code. And so that's one way to accomplish everything. So I'm going to show you, we're going to have to hook this up though quickly. So I unhooked this mess that, if you were watching the previous videos, was attached to the board. That's for the final circuit, the Simon Says project. But for this one, I've created the RGB LED on a separate breadboard here, and you can see, hopefully, there's 4 pins on the RGB LED. The second pin in, which happens to be the longest pin, is attached to ground, with this ground rail, which I've got a black wire hooked up that will hook to the ground on the microcontroller. And then the pin right next to ground is the red pin, and then on the other side is the green, and then the far end is blue. And I've shown those connections with the appropriate colors, red, green, and blue. And they're also, because they are all individual LEDs inside this one housing, this RGB LED housing, they still need resistors just like any LEDs do to limit that current, so that you can protect the sensitive LED. So these are 300 ohm resistors. You could use 330 ohm resistors, but I happen to have some 300 ohm resistors, so that's fine. So I'm going to hook this up. I'm going to look in my code and see what pins I had those attached to. So I'll go look at my constants. So the red LED is on pin 5, green is 6, and blue is 7. Okay, so we'll do that. We'll hook that up. Red was 5. RGB, green was 6. And blue was 7. And then make sure we hook up our ground. So there's a ground over here. So we'll do that. Let's just leave it like that. And we're going to hook up this. I'm not sure if it's already working. Okay, so I'm going to bring up the code side by side so again we can see what's happening. So it looks like I neglected to write what colors I was going to print these in. But basically, I did do it in some other code, so maybe now's a good time to go over that code. So I didn't tell you what colors were going to happen here, but basically, if I press button 1 by itself, it's going to be red. Button 2 by itself, it's going to be green. Button 3 by itself, it's going to be blue. Red and green together make yellow. Red and blue together make purple. Green and blue make cyan. And all three of them make white. So that's, and they all have different tones as well. So the combinations have different tones. So this is red. So red is the LED, which doesn't really show up on the camera very well, but that is red. That's green. That's blue. And there's a different tone with all of them. When I combine red and green, that's yellow. And a different tone. When I combine green and blue, that's cyan. And a different tone. And when I combine red and blue, that's magenta, purple. Which again, doesn't really show up on the video, but it looks great here. And when I do them all, it turns white. So again, I'm looking at both the videos the same. It looks great at the angle I'm at in person, but it doesn't seem to work right there. Oh, and I've disconnected the ground wire. So that's yellow. That's purple. That's cyan, and this is white. Either way, it doesn't seem to be showing up great, but you get the point. It is the you can trust me. It is the different colors. But I'll show you the other code. So there's two options. One, you could use binary math, which is this, and the other option is to use if-else statements with Boolean logic. So we're going to do that right now. I'm just going to comment out the binary math option. Actually, so this is, instead of using binary math, I'm just using plain old if-else, if-else-if statements, but I'm and using Boolean logic. So quickly, it's accomplishing the same thing, but it's using if-else statements. So if first button, I'll go over this first one. If first button pressed, and this double ampersand is the Boolean logic operator, and it means if this is true and this is true, both things have to be true for the whole expression to be true. If either of them are false or both of them are false, the whole thing's false. So again, both things on the left and right side of the Boolean and Boolean and operator, this double ampersand, have to be true for the whole thing to be true. So what's happening, I'm checking if first key pressed and not second key pressed, if both those are true, meaning if the first key is pressed and the second key is not pressed, because we have this not symbol in front, if that's true, that'll evaluate to true if both of those things are true, meaning the first button's pressed and the second one isn't. But then, this already evaluates to true or false, whatever happens to evaluate to, and then we check that against and not the third button pressed. So basically, this is only going to, we're only going to go and call the play tone function, passing in note C as the argument. So we're only going to play note C if the first button is pressed and neither of the other two buttons are pressed, i.e. just the red button is pressed. So in this case, this is what that if statement is for. If just the first button is pressed and neither of the other two. Else if not the first key pressed and the second key pressed and not the third key pressed, meaning only the second button is pressed, then we're going to play note D. So again, that. Else if not first key pressed and not second key pressed and third key pressed, so only third key pressed, we play note E. And then it's combination. So again, the first two keys are pressed, we play note F, and then the first and third key are pressed but not the second, we play note F, and then the second and third are pressed but not the first, so not first key pressed. So again, first key press is going to evaluate to true or false. In this case, it's going to evaluate to false if we didn't press it, but not false is true. So we need the first key not to be pressed and the second and third keys pressed. So this. That's note A. And then finally, if they're all pressed, we'll play note B. And obviously, I've just added the RGB color for fun. Else, if none of these combinations are pressed, meaning no buttons are pressed, then we're just not going to have the buzzer. We're going to call the no tone and buzzer. So again, I apologize for the lengthy video. This was only actually supposed to be showing the circuit, but again, not a content creator. I've said that a bunch, but it bodes true now as well. So I'm going to stop the video here after going over the just the quick considerations from this circuit 2B, and then I'll start another video for circuit 2C. So the code challenge for circuit 2B, this is what we accomplished. Explanation of the code, I basically added constants and modularity to my code. Again, I love using constants instead of magic numbers just because I find it makes it more readable. So again, if you look, I know what everything here is. I know that, you know, when I'm setting up these pin modes, oh, these three are for the button. Not just because they're inputs and pull-ups, but because it says first key pin. Okay, where the first button is. I know these are the LEDs. Red LED pin, green LED pin, blue LED, this is buzzer pin. I like using constants because they're like note C. Oh, I know this is, what am I passing into this play tone thing? Well, note C. Why? Because we have constants for that. And constants just make code more readable. Red state, okay? I like the... so that's why I'm using constants. So let's see, use constants and modularity. That's just when I break things up. That's where I even encapsulated the tone function inside the play tone function. You know, you could argue that that's, you know, becoming a little verbose and not like making it unnecessarily convoluted, but I like sort of separating code and encapsulating that way and just making it more readable. Almost like when you're going down your program, you just read it like pseudocode. Note frequencies are stored as constant, allowing easy modification. Yeah. In setup, we configured the buttons as input pull-up, just again using the internal pull-up resistors associated with the RedBoard microcontroller. Button combinations, we did both Boolean logic using the double ampersand symbol operator, so that's for Boolean and we also did binary math, where we multiply each button state, whether it's push or not, by a unique weight. First button had a weight of 1, second button had a weight of 2, and third button had a weight of 4. Again, if you're not sure fully still how we did that, just look up binary weights and, you know, binary counting, and that'll sort you out. And then and why did we do this? Well, we did this so that we could have only 3 buttons, but we could actually create 7 different combinations. 8 technically if you count off as a combination, but we could play 7 different tones and light combinations, colors, with just 3 buttons by using the principle of 2 to the third. So the binary, each button had a binary state, 2 states, and 3 buttons, so we had 2 to the third combinations, 8 combinations. One of them being off, and then the 7 other ones that played the tone. We generated tone with the playTone function, which basically just wrapped up the tone function, encapsulating that behavior for improving code readability. And the no tone function works as normal, just stops the buzzers from making noise when buttons aren't pressed. As usual, I use Doxygen comments with my special Doxygen tags. Not mine, the Doxygen tags. So @file, @brief, @param. So this is the name that your file. This is just @brief. It just indicates the brief description to be displayed somewhere. You can also have it @detail, which is a detailed description. @param, this @param for parameter, etc. And that just helps you create professional grade documentation automatically. RGB LED configuration. Again, it's just an RGB LED is simply 3 separate LEDs, a red, a green, and a blue LED, all housed in a single LED housing, but it still has 4 pins, 1 common ground, and then 3 of the positive pins associated with each of the LEDs. setRGBColor function that does that. I should probably be going through this quicker. The color logic, again, you press the single red button, the LED glows red. The green button glows green, blue button glows blue. If you press red and green together, the LED glows yellow. Red and blue together, it glows purple. So again, red and green, yellow, red and blue, purple. Green and blue together, it glows cyan, and all of them together, it glows white. Modular coded. Oh, and why did I add this RGB LED in the first place? I actually did it, I say because it's fun, which it is, you know. Adding color to any project is always fun, but mostly because I'm tone deaf. I actually just am horrible with music as far as hearing, even when we watch American Idol or something, or any of those shows, I can't tell if the person's sang good or not if it wasn't for watching, you know, the audience's faces. And even then, sometimes not fully sure. So I'm tone deaf. So I added the color actually for myself because when I was pressing the 7 different combinations, I wasn't sure if I was getting 7 different combinations. So I actually had to add the color for that purpose. But you know what? It's also fun. What are some future improvements I could do? You could add some debouncing logic. So a lot of these, I haven't been adding debouncing because my videos are long enough and convoluted enough going through the simple code. But obviously, when you're dealing with buttons, you want to use debouncing logic. You could do simple debouncing logic using just delays. You could use time functionality where you're using a combination of the millisecond function, which you basically call and get the time at the start, and you create a couple different variables for previous time, the last time the button was pressed, and you know, get the time now every time you enter a loop, or every time you press a button, you get the time now. You compare the time now with the last time the button was pressed. Is it greater than some, you know, debounce delay, like of 50 milliseconds or something you've created, and you basically don't read the button for a long time? If you're not familiar with the time, how would you use time functionality to debounce buttons? Make a comment. I'll feel free to upload a video. Again, make sure you have a weekend to watch the single video because I'm really long-winded, I guess. But you know, obviously you can use software to use debouncing, or you can create debouncing via hardware. Just Google how to do that. There's lots of different ways, especially with these little crappy momentary buttons that come in these kits. They're not very great. If you pay a little more for buttons, you'll probably get debounce hardware already incorporated in the button, but you can still create some with these buttons as well. So that's an option that you could do to improve this. Also, you could create dynamic tempo control, your beat length, using a potentiometer. I did that in a previous coding challenge, so I didn't do it in this one because I have to keep moving the potentiometer that I have. But that's pretty much it. So, and yes, testing and enhancements. Basically, just verify each button in combination, light up the correct color, and play the correct note, which that's why I added the RGB, because I wasn't sure if that was happening. You could also add smooth operation transitions. I did that in a previous, have the LEDs transitioning smoothly using the RGB LED. I did that previously, so I didn't do it here. And yeah, the coding challenge program now provides both auditory and visual feedback. So the auditory feedback is what the coding challenge actually called for, and the visual feedback is just what I'm doing through the RGB. And then that's pretty much it for this video. We'll come back and we'll do Circuit 2C, which is the Simon Says game. Again, thanks for watching and sticking with me.